Should we close the door? Okay, so welcome all. We have our second lecture of Map&Models, and this one is entitled Data and Information. So, the last lecture when we did the introduction, we introduced you a similar picture as we are having here. So this is the natural communication model. It was created by the mathematician and physicist Elias Safiris. And in this mathematical model provides a framework for representing and solving a wide range of scientific and technical problems. Safiris stressed the idea that in nature we do not have access directly to it, so then therefore we have to create a model. And the thing is that the things in nature are always encoded in geometric structures. So the purpose of this model, according to Safiris, is to reduce complexity and create new information. So in the simplest case of a model, it contains an encoding bridge and decoding bridge, and they are both necessary for establishing communication between these two levels, which he identifies as geometry and harmonics. So to come back to the concepts of this course, we said the last lecture that the model information is the specific render of a map data that comes from the world reality. And these concepts are always in a cyclical movement. So however, in order to communicate these two levels, we need to build these encoding and decoding bridges, and we are proposing that these bridges should be the encoding bridge and machine intelligence, and the decoding bridge intelligent humans. So this lecture we are going to talk about information, data, intelligent humans, and machine intelligence. So what is information? The definition of information through time had different meanings, and they were always bounded by the current technology and beliefs of the time. So if we check the etymology of the word, the meaning stems from an act of informing, instructing, to shape or to give a form to. So today's physics and technologies are pointing towards quantum mechanics and thermodynamics. So quantum mechanics is the physics that studies subatomic particles, which are the atoms, and thermodynamics it studies the conversion of heat into energy or energy into work. So if we see in thermodynamics, we have the first law that says that the energy of the world remains constant. The second law is that the entropy of the world tends to a maximum. So if we focus on the second law, stressing that entropy is the tendency towards disorder in a system, it will help us to draw this analogy and to answer the question regarding information. So if we know that entropy can make reference as data, so we can think as the negation of entropy, or a term that was introduced by Schrödinger and in detail by Bullman, a negentropy, which will refer to information. So we can say that with full entropy, we get zero information. So this is what we call a stable system that is in stasis. So we can get nothing out of a system in stasis. It is dead. But with zero entropy, we get full information. One thing that is important to know is that there is no fixed meaning in information. Actually, what is important is that we can articulate the meaning out of this meaningless data, which is entropic and which we have plenty of it. So in this sense, information will be the articulation of meaning out of this meaningless data. So also, we will have to define information in the digital world. So first, we have to identify the differences between the basic element of information and communication, which is the bit. So if we make a difference between the technical representation of the bit that we see in our computer, between the binary number system from Leibniz and Boole, which is the logical ground of loss, which is in true or false. So as a technical representation, what we are seeing in the right is a rendering, is a positive form of body, and is a geometry. But then if we think of it as this loss of thought, it can be an expression, it's a logical source of thinking, and it can be folded into anything. So we always have these two sides. We have a representation, and then on the other side, we always have this ability to become something. So this is that we can think of the bit, and we will see it more clearly in the experiment that we're going to have at the end of the course. So therefore, a bit is always the distinction between nothingness and anythingness. So you can articulate meaning by using this small, by using the bit, which is the smallest part of information. So important also to know is Michel Serres introduced the notion of universality in information. So he said that we do not know any living being of which we cannot say that it produces information, receives information, stores information, and treats information. So there is this quadruple characteristic in common between all objects of the world that are living or inert. So meaning that anything is active, anything engages with the world. So if everything produces, receives, stores, and treats information, and if anything can be transformed to anything, we end up with entropy, this disorder that we talked at the beginning. So, and that we refer that as data. So therefore we can say that we end up with a large amount of data, and it feels that we are being flawed with it. And the more we get, the less and less it makes sense. So data has no meaning per se, and it is a symbolic representation of something. So if we look back at the history of computation, we have gone in a wild movement of decentralization from mono-functional machines to a world of applications. So we have gone from one computer, many people in 1943 to one person, one computer in 1974. And today we have reached a radical inversion with one person, many devices. By 2002, humans have produced 2 exabytes, which is billion bytes of data. In 2009, 260 exabytes. And nowadays, the digital universe is made up of more than 1,200 exabytes. And 90% has been produced by the last 2 years. And it's been estimated that by 2020, we will reach a total of 44,000 zettabytes of the data produced. And these are data that are generated when we work, when we consume, or when we travel. And it's produced by individuals, either intentionally via blogs, social networks, and discussion forums, or unintentionally with the interactions online and offline with the digital world. So all these movements, they leave digital footprints, and they are often collected by default mechanism to monitor online movements such as Internet of Things, social media, GPS tracking, traffic flow monitoring, or satellite images. And these data are often described by 4 characteristics, which are volume, velocity, variety, and recently value was added to the list. So just to give an example, today every person has 320 times as much as data as it was estimated to have been stored in the Library of Alexandria that we're seeing in the picture. So the Library of Alexandria was the largest and most significant libraries of the ancient world, 3 centuries before Christ. And as I said before, just to stress this idea, the digital world is today made up of more than 1,200 billion bytes. And it's amazing that only with the last 2 years we have produced 90% of it. So variety in data. Big data can have 3 types of variety. So the first is the variety in formats. So there is text, images, sounds, geolocation data, mobility data, etc. Second, it has variety of sources, so it can come from many platforms and many users and stakeholders and beholders. And the third variety is on structure. So data can be unstructured, semi-structured, or structured. We have the third, which is velocity. So data is being accumulated and stored in real time, all the time. And the last is the last that has been added recently is value. So data now has become a key input for driving growth. So it's enabling now business to differentiate themselves and maintain the competitive edge. So since now users' data has become more an important asset, because companies now they like to profile their users in order to address specific products depending on a specific preference they have. So now we're going to talk about what we define intelligent human. So we have here a quote from Descartes. So in his book, A Discourse of a Method for the World Guiding of Reason, he sets the path to define an intelligent human as the one able to reason rather than how educated he or she is. So Descartes does not refer to an educated man, but to an intelligent one. According to him, we are all intelligent because we can reason and understand. So I will just read this quote. So he said, "It is almost impossible that our judgment could be so clear or so solid as it might have been had we had the entire use of our reason from the time of our birth and been always guided by it alone." So we argue that intelligent humans embraced obstacles. So intelligent humans are deprived of computational power, but they are capable of articulating complex problems, reasoning, understanding, and taking ethical stance. So I wanted to give just a quick example of what I mean when I'm saying embrace obstacles. So when a baby is born, he needs to embrace obstacles while he's growing. So the first one is gravity. So the parents, they don't think the baby has a problem because he's not walking. They know eventually he will embrace gravity and he will start walking. And it's the same thing with language. So we don't think he has a problem because he's not speaking, but therefore with time he learns and then he embraces the obstacle of communication and then he eventually speaks. But this is actually the main difference with machine intelligence, because from the beginning, machine intelligence, they were always designed as a problem-solving tool. So they don't have to embrace obstacles, they only need to achieve a task which is already predefined by humans. So that could be the main difference between these two types of intelligence. And the sense that we are calling it intelligent human and machine intelligence is actually emphasizing that we are so different that cannot be compared in the same level. So the thing is that we are, if we can put it like graphically, we are not in a parallel sense, we are always perpendicular. So the idea is that with both type of intelligence, we can actually strive now in current days. So machine intelligence can be classified into two approaches. One that seeks to reduce human intelligence to symbolic manipulations, and the other that tries to mimic the model of neural behaviors and build a mathematical model for it. So in both cases, machine intelligent algorithms are seen as this problem-solving tool, which is attuned to a specific set of problems. Another thing that is interesting to see is that now, even now, machines are not only solving problems, they are de-solving problems. Because with big data, any question can be answered. So there is not a specific problem to answer. These machine intelligent algorithms, they can solve any. So how machine intelligence have been designed, it always evolved through time. But how we as humans think or reason, it was always and will always be in the same way. So that's also a way to differentiate between these two types of intelligence.
that's my turn. I'm quite nervous actually. So, so I would like to give a brief and quick introduction of how artificial intelligence and what we call machine intelligence was developed in the last let's say 50 years in order to better explain our concept of machine intelligence and intelligence human. And it's a very quick show and very quick guide. So at the beginning of developing the artificial intelligence or machine intelligence, a core topic is what exactly intelligence means by us. And actually this is a very ambitious question, and actually I don't have an answer yet. And also there was quite a lot of debate on exactly what intelligence should be and how it should be implemented if we try to create an artificial one. But then British scientist and mathematician Alan Turing, he get annoyed by this fruitless discussion about the meaning of the words. So he actually suggests another approach that was accepted by most of the people. So simply he said, let's forget about this meaning, and then he proposed a test. So so this is a text I quoted from Alan Turing's publication called Computing Machinery and Intelligence, published in 1950s. So in this paper, he proposed an imitation game. So I will simply read it. So the game is played with three people: a man called A, a woman called B, and an integrator called C, who may be either of sex. And the integrator stays in the room that apart from the other two, and the objective is to determine which of the other two is the man and which is the woman. And so during this game, the integrator will try to ask some questions, and both the man and the woman will try to answer these questions. And by these conversations, the man try to deceive the interpreter that he is actually a woman, and the woman will try to persuade the interpreter that the other guy is false and she is actually the real woman. And so what Turing proposed is that what happens if we replace the man A to a machine that is able to talk, and would the machine let's say produce a convincing result that actually confuse the interpreter from distinguish who is who. And this is basically the core idea of this game. And Turing suggests that if the machine is capable to reach the level that, let's say, the level of to reach the average level of a man being an A can produce, then we can believe that somehow this machine is act intelligently. So this is the basic idea of this game. And then further we can, if we follow the idea of this game further, then we can reduce this game to a question and answer loop. That basically we have an human interpreter, and we have an object sitting in another room, which can be a machine or can be a human. And then by asking questions and getting answers, as the interpreter should determine if the object in the other room is a machine or not. And as Turing said, that the question and answer method seems to be suitable for introducing almost any one of the fields of human endeavor that we wish to introduce. So basically this is the idea. And if the machine is capable to persuade the interpreter not to persuade, to confuse the interpreter from determining if it is a machine or not, then we somehow believe that this machine acts intellectually. And so following this answer and question loop, we can actually think about that this question and answer does not necessarily to be in text. Actually, it can be in any format. For example, can be pictures, can be a specific task. For example, how well these objects in another room can play chess, for example, or classify pictures, or drive cars, or making conversations, and so on and so on. So eventually, we made a conclusion that that basically this question and answer process would be a task for the object in the other room to solve some particular problems, and we think that this is the origin that why machine intelligence was eventually end up with problem solving. So because this is the way how Turing suggests we can determine if an object is act intellectually or not.
So Turing was the first scientist that called machine intelligence the type of intelligence that we're going to describe today. And this test, the Turing test, has been performed until today. So it's yearly, there is this interrogator that is behind the curtain, and currently like a machine and a man who are responding questions, and then the interrogator has to know which is the man and not. So every time they lose or win, depending on the algorithm they use to pass this test.
And then after accepting the setup of this game, then people began to wonder how exactly we should approach this machine. And in particular, nowadays, instead of being an integrator personally, so we do this game by comparing the output result produced by the machine with the result that are produced by humans, so that we simply look at the result to see if they are similar or not, instead of personally being there and asking questions. So in the following slides, I will briefly do a very quick sketch on the different approaches, how scientists address this, how scientists realize this kind of machine. And then first, if we think on an abstract level, on a mathematical level, then we can regard this question-answer loop as a function that whatever question we have, this function will produce an answer. And then the problem is, can we find a mathematical function that always give us satisfying answers for different questions? And if we visualize it, this is a very simple visualization. If we think about it one-dimensionally, then our question may be one number, and our answer may be another number. Then we can plot our questions and numbers with a scatter plot on the left. And then if this function actually exists, then this function becomes the blue line on the right that connects all these red dots. So basically, with this function, you can not only answer the questions that you already have, then this function, in principle, can also answer some other questions that are not exist before, for example. And then, of course, these questions and numbers need not to be just one number. Actually, it can be many things. For example, the question can be a text, and the answer could be an image, and so on. But then we will illustrate later that basically, with a computer, all these different formats of data are in principle numbers. Therefore, the machines are always operating on the level of numbers. Yes. And so then how exactly we should do it? So at the beginning, the very core question is whether we should do it by simulating our brain or not. And then there's no solid conclusion regarding this question. And then following this question, there are two branches that are produced by this question. One branch is believe that we do not necessarily need to simulate our brain, but instead of we should try to making abstractions on how people reason about things, or how our way of thinking works. And then the first branch showing on the left, eventually we can say that it's towards a symbolic manipulation. So this branch believes that human thinking can be reduced to a set of symbols, that a set of symbols and the combinations of them. And then this branch gave us gave us approaches that I called here logic-based. For example, it could be a rule-based system, or it could be a decision tree that has many if-else decisions. So for example, if something happened, what should do? If something else happened, what should do? So basically, this is the idea of this symbolic manipulation. So basically, every symbol represents, let's say, a decision or a condition. And on the other approach that the people believe that we should actually simulate our brain in order to achieve such a machine. And then, therefore, at the beginning, there was a model called artificial neural network was proposed, and it is actually a mathematical model that was inspired by how neural cells are connected in our brain. And then later, this approach separated into two subdomains. One focused more on the mathematical abstraction of such setup, and the other is actually trying to see if this setup actually explains how our brain works. So the one is more on the abstractive level, and the other is trying to explain how the reality is. And then the major contribution of the artificial intelligence nowadays come from the first sub-branch that focus on more on this mathematical level. And then at the beginning, the second branch, the branch on the left, actually doesn't work because I will explain later briefly. Because this setup will introduce millions of parameters that at that age, scientists have no idea how we can determine the value of each parameter, because it's just too many. There's no way to do it. And on the other hand, the logic-based approach actually, because it's very clear, you can talk about it, you can reason about it. Therefore, at the beginning, the first branch reached a great success. But then after that, when we are facing more complex problems, we find that the first branch actually not anymore working because of certain limitations. For example, the combinatorial explosion, and then also the development of computer science introduced some more algorithms. For example, the gradient-based training algorithm that allows us to determine the value of millions of parameters. And then after that, there was a shift from logic-based to this probabilistic-based. And then after that, the second branch get boosted and was eventually becomes the AI that we see on the internet nowadays. So I will first quickly go through the first branch. So it's the logic-based system. So here shows a very simple case that for example, to imitate how human behave. For example, I can say first I would like to ask, am I hungry or not? If I'm not hungry, maybe I should go to sleep. If I'm hungry, then I will probably find some food, and what kind of food I have maybe depends on how much money I have, and so on and so on. So basically, it's a if-else decision, and we can, for any type of problem, we can try to think about as many conditions as possible and link them into a tree-like structure. And actually, this diagram showing on the right was called decision trees. So basically, the idea is to link these different conditions together so that we get a logical representation of solving specific problems. And the most prominent example of this approach would be the Deep Blue. It was a chess playing computer developed at 1985, and in 1996 it had its first chess match against a human chess champion called Garry Kasparov. And at that time, this machine, Deep Blue, was defeated. But then in 1997, the scientists made some modifications, and the matches was held again. And for the second match, the computer actually won. But if we look deeper at how exactly this machine works, basically it was a brutal search algorithm for what could be happening in the next let's say 10 or 20 steps, because for the computer it is able to enumerate more options than a human can, because it becomes really complicated for us to estimate what happens 10 steps after, because the computer is able to enumerate them and to memorize them. Therefore, for computer it's possible to choose the optimal solution among these 12 more steps. Therefore it is able to beat the chess champion of human. But then at that time, scientists claimed that this was the real intellect. But then nowadays, if you see how really how this mechanism really works, then we will for sure we will no longer believe that this is actually intelligence. This is simply brutal search. So this was a very prominent case, and also the similar case can be solved on the bot players of different video games. For example, these are some video games that was popular when I was in high school. So yeah, but in principle the idea is the same. For example, in Warcraft 3, if you see that the bots leading an army towards you, and if you don't hit them when they were marching, they will never hit you until they reach the destination. So basically, this kind of pattern you can observe by playing with the computers, and if you catch these patterns, you can always win, and the computers can never involved by, for example, if you attacked a computer's army during its when they are marching, they will not let's say counterattack for the second time. They will never remember this experience. They will always follow what has been instructed. So this will be the case. And to conclude, Haugeland, he conclude this branch of artificial intelligence as the good old-fashioned artificial intelligence, or in short, GOFAI, G-O-F-A-I. So he said that good old-fashioned artificial intelligence as a branch of cognitive science rests on a particular theory of intelligence and thought, essentially Hobbes' idea that ratiocination is computation. So this logic-based approach was so successful before 1970s or 1980s, and actually there was quite a lot of people that believed that this was the golden path towards artificial intelligence or machine intelligence. But then when we are introducing more complicated tasks, these approaches actually faces difficulties that can extremely hard to overcome. For example, the explosion of the search space. So for example, if we compare these two games, on the left is the chess, on the right is the Go. So because the search space of the Go game is much larger than chess game, then making it impossible for computer to brutal search every possible option within a reasonable amount of time. Therefore these logic-based rules never works for the Go game, and the human and the Go players always believe that this is the last standing ground of human intelligence that cannot be addressed by automated machines. So this was the difficult part. And also, if we think about different tasks like trying to identify objects from pictures, then we have similar situations, because all the objects in the pictures are actually represented by pixels, right? And not just one pixels, but a collection of many pixels and the correlations between them. But then the problem is, for the same object, it could be appears in a different location, different size, different angle, different different condition of illumination. So basically, it's impossible to write down specific rules to how to let's say, by determining which pixel is which value, that tells us which object is in the picture. So basically, this is impossible, and therefore scientists becomes to ask: is there a way that instead of making explicit rules, that we can find the inexplicit correlations between the image itself and the answer we want to have? And this is where the second branch actually was taken back again. So and also this branch was supported a lot by the advance of proper training algorithm, which I will just briefly talk about it in the following slide. And also it is note to mention that this branch is always probabilistic based, and it's always data driven. So because you learn the probability from data, but not from let's say rules
Already
anymore.
defined rules.
Yeah. And so I would like to first point out that for this branch there are many different algorithms, but then because this branch starts with the idea of simulating the brain, so I would like to introduce what artificial neural network actually is. So so if we search artificial neural network on the internet, we always find similar diagrams that are showing like this, which looks somehow like a real neuron. But the idea of this is that for each circle here, it consumes many numbers and do internal calculation and gives the output of as another number. And we can combine this basic combine this basic element together into a large network. And in principle, for example, on the right, every black arrow on the right is the conversion from 3 numbers which is shown as red circles to 2 numbers which is shown on the blue circles, green circles. And in principle, on the right, every black arrow will be one parameter that need to be determined. And because at the beginning the number of these parameters are so many, because here is just a very simple case. If you make a similar setup for more complicated problems, then the number of arrows will be much more. So because it's difficult to determine which value should be given to each to which parameter, so at the beginning this method simply doesn't work. But then the back propagation, there was an algorithm called back propagation, which is basically a gradient-based method that allows you to do gradient descent for this setup, and then this algorithm, the introduction of this algorithm actually solved the problem of giving values for each parameter, and therefore it's possible to let's say train this structure with some data, and then it was and after that this setup was actually boosted. It's really based on this gradient-based algorithm, and also because the internet is now more and more well established, and also the data produced by internet also make it possible to have a large amount of data that are also necessary to train such structure. So basically, this is how this let's say mathematical model was developed. And we will not introduce further regarding the technical details. And if you are interested, actually a colleague of our chair, he is doing another course. He will introduce detail how exactly these calculations were done for this particular setup. Yeah.
Here. So if you actually want to know the mathematics and how to build these networks, you can join this lecture. So he will go from the beginning, and then this lecture is meant to be for architects.
Yeah.
And he will introduce all the mathematics and the models of it. So just quickly, I just wanted to say that what we are seeing here with these neural nets is not recent. So it was even at the same time as the Turing test. So
it was very old. Yeah.
And you see now back propagation, the one that enables it to be trained with data and learns the characteristics of it was from 1975. So it's not new. And the thing is that we actually think it's new, like from 2017 till now. It's because we now have the power and the computational power and the data to train with them.
Yeah. And also it was why such setup works, because as I just showed this diagram before, that actually this kind of setup is one of the what is called universal function approximator, which means with sufficient amount of parameters, this setup is capable to approximate any mathematical functions within any precisions. And this is why this setup works. But also there are different function approximators, and for example, regressions or linear regression or nonlinear regression can be also belongs to this category. And so what is deep learning then? Deep learning is a very hot topic nowadays. So simply deep learning is neural network with many layers that people call it deep, and this is the whole story. And because the efficient training algorithm we have, and the GPU acceleration we have now, it's possible to build and train a very large neural network with one PC, and therefore this method got popular and was investigated by researchers from different disciplines. So as an example, I would like to go back to the Go game, to the Alphago, and quickly explain how Alphago works. So instead of explicitly write down the rules of how to play a Go game, Alphago learns the patterns from human player. So in principle, at the beginning, the development team of Alphago collect many, I don't know how many exactly, many records of Go game played by human players, and they match every input to every output. So for example, the input would be the current state of the Go board, and the output would be where to put the next step, for example. And then with this data, plus a neural network, which is a mathematical model now, the input was, for example, converted to an image, which is in principle many numbers, and was fed to this neural network, and the neural network will give an answer as the output. And then the problem is to see how error the prediction is from the actual movement produced by the human player, and then to calibrate this whole network using this error. And then the idea is to do this process millions times iteratively, and so that the parameters of this neural network converge to a very stable status, so that the output is somehow calibrated to the output that a human player would have. And despite the two branches I've been introduced, there are also another approaches that somehow lies between these two, because I made a clear distinction that the first branch is logic-based and the second branch is data-driven and is probabilistic-based. And actually there's a third method called probabilistic graph that is somehow both logic-based and data-driven. So I will use this this graph to quickly explain what the probabilistic graph is. So basically, it is a graph that the causes and the consequences are predefined by human researchers. For example, what caused a grass wet, and so on and so on. But then the probabilistic distribution from different causes to different consequences was observed from the data. And also we can transfer this. We can transfer the what's the word of that? Decision tree showing on the left to this graph showing on the left by simply observing by observing many people how different people react on the same problem, and then write down the probabilistic. So basically, this is the idea of this probabilistic graph. It's a fixed topology, but then the data of this graph was was counted from the data we have. And then following the brief introduction of different approaches, we can also quickly look at the different applications we have nowadays. For example, self-driving car. So basically, the idea of self-driving cars is exactly the same as AlphaGo. That you have a car, you install many sensors on this car, so that the sensors reads the environment, so that the sensors provides readings to the computer, and the computer on the one hand record these readings, and on the other hand observe how human driver drive, and therefore you have a large amount of data. So on the one hand is the sensor reading, and on the other hand is the human's reaction, and then you learn the pattern from one to the other with one of the methods I've introduced before, and then if the learning process working well, then you have a mathematical model that is capable to produce, let's say, human level reaction from the sensor reading of the car. And then if you put this machine, if you give the full control of this machine to a car, then this car becomes self-driving. And also for the task of object recognition is the same. That at the beginning, researchers manually labels many images with the position of different objects. So millions of images were labeled in a similar way, and then was fed to a mathematical model to be learned, and then eventually the result will be something like this: that the machine is capable to tell, for example, which object at which location in the image. But then the problem is the output of this machine is always limited by its we call it training data, the data that are produced by humans. So if we are not telling them, if we do not label, for example, horses at all from all the images, then the machine will never tell that there's a horses in the image. So the output is limited by the training data it has. And also this application of to pixel level labeling of images. So the computer is able to determine which pixel represent which type of objects, and so on and so on. Yep.
So right, so we introduced you 4 concepts, and the last 2 were around intelligent human and machine intelligence. And the idea that Gu has stressed on the training data is really important, because it means that the machines are learning within a specific framework. Yep. So if you create a training data which only that is full of cats, it will only learn about cats, or full of cars, only cars. And also now there is one algorithm that goes beyond AlphaGo, which is called AlphaZero. So this algorithm, it's not learning within a training data, because it's learning by this brutal search of how logically a move should go. But still, it doesn't reflect how we actually create memories, or how we actually reason about the things. So what we want to stress is that this conjunction between intelligent human and machine intelligence, it's important now with the current abundance of data and artificial intelligence algorithms, because the aim is neither the resolution of all the problems by assigning all the responsibilities to machine intelligence, nor setting projects that are based only on intelligent humans. So because these 2 types of intelligence, they have specific assets and capabilities that should be brought together, so they both can interact and they both can win in the process. So we bring, as we promised the first lecture, we are bringing questions at the end of the theory part, because we actually want to trigger your interest and actually know what you think about it. And then if you actually understood, or is there things that maybe needs to be further explained. So this is the first question. So what is the role of machine intelligence in design and architecture? So if you could react, the first thing that comes to your mind. So will it take over? This is like, what is the
this is like what.
But you have it in the internet, not unlike what a lot of people are saying. So if someone has something to say, it'll be very nice. What do you think? It's just the first thing that comes to your mind.
Yeah.
So will it change architecture? Will it not change architecture? Will it replace us or not?
Yeah.
You want to say something?
Yes.
I think it will drastically change how we work. I don't think that it will completely replace us, but I think it will help us to get like a huge spectrum of, and then how we interact with this spectrum. I think this will be really different. So.
Yes, we actually think the same. So if we give an example of how humans have evolved from this agricultural revolution, when we stopped being nomads and gathering fruits, to having agricultural fields where we could actually stay in one place, and then we had this second revolution, which was the industrial revolution, where the agricultural fields were replaced by machines or by industry, and then all the people who were working there, they had to do something. Therefore, they were working in industry or in machines, with machines. So now I think we have this new revolution where we don't have to be in industry anymore, because this can also be replaced by this machine intelligence. But then what is the thing that we should do next? So what we actually think is that we have to be aware of that this change is happening, and then we have to be educated enough or illustrate or literate in the sense on how we can actually gain with this process and how both type of intelligence can work.
Yes.
And if you're saying that machine intelligence is trained or learns based on what we tell them to learn, then we will always be in control, right? If we tell them that they have to learn a specific subject because it's based on what we currently talk in internet, then it will always learn how we speak or how we talk. So we can actually have control on that.
Yes.
But don't you think then that machine intelligence, when it comes to sheer developer architecture, will kind of replace the whole process from design to construction? As when you look at standard architecture, it's basically standard questions that can be easily tackled by machine intelligence. Design a standard office building that is efficient, energy efficient, space efficient, etc. So I think that this developer architecture will definitely be this kind of one area where human action is being replaced by machine intelligence, and that production of space and architecture generally will be accelerated by that in a very, very strong amount.
I think exactly when you talk about the standardized spaces, then this could be a work that the machines can do, because they don't need to be, in a sense, creative. If we look back on history, how the best discoveries happened, they were never logic at the time. They were always coming up without logic, or things that just happened to be like that. Or we call it serendipity, which is the thing like just, it goes there, it's just against every logical path, but it just comes to be. And I think maybe now we have to be more aware of this, which are the tasks that we as humans can produce better, and then just focus on that. Because, for example, I just have this idea. In China, they have these skyscrapers.
Yeah.
They can for sure be produced by machines. Like small details, we don't have to care anymore, because they should be produced fast. They should be correct. They have to be all of these things that machines are better on doing. They can actually do that. But I think then when you try to design something which cannot be standardized, or it just has no rules, then I don't think this is the place of a machine.
Yes.
I don't really think that the question is whether it's standardized or not. It's the other question is like, would machine intelligence take over? And I don't think so.
Great.
With the current technology, I think the role of the architect changes because he uses the tool, machine intelligence, and he gives the computer parameters. For example, a line, like 50 years ago, you would draw a line with a pen, you would draw the whole line. And now you just draw 2 points, and the line is generated. And in the future, you can give more parameters, and the computer will generate more options. And as long as the architect can work with that tool, machine intelligence will not take over. But as soon as the architect cannot work anymore, or doesn't understand the tool, he loses the job.
Exactly.
I think that's exactly. I mean, this question was very provocative. We don't actually think that's the answer is no, for sure. And how you frame it is how we think. So we have to evolve how architects are currently working now. And many tasks that are happening in architectural offices now, they can be performed by machines easily. Just the things that we don't know how they are working, and that's why
how to work with
a lot of architects and a lot of people are afraid just of the word AI. So it's like AI, no, just don't. No, I don't. I like the pencil, and it's just. So it's just if in architecture becomes a word that you're not afraid anymore, then you actually start like, taking it and working it, and it's not scary.
And also, it's interesting that I know that nowadays in China, Chinese architectural industry begin to introduce this automated machine into the design process, for example. But not, but they are claiming that this is artificial intelligence. So, but then the story is always trying to optimize the, let's say, the layout of the building within the site, or the distribution of different functions in the building, and so on and so on. But then it's it's already happening that that this kind of tools begin to be introduced in our working flow, and then I think it's important to that we learn about it. We know how this thing works. We know how to deal with it, and then we should think about it. What will be the new question for us then?
Yes.
I think, or I wonder somehow if the way I imagine it is that you have certain project, certain building, and you know parameters, the size, the requirements, whatever. You enter them into the program, whatever it is, and then it presents you with options. And then somehow you have to be able to evaluate, or you have to be able to decide which option is best. And this somehow, at the moment, I don't really know how this will work. I mean, this is something completely different, because before you come up with a project with a process, and every decision is somehow, or should be, informed by either an idea or data, and then you reach a certain result. But you skip the whole process, and then you just have the result. And how can you decide which option is the better one, or the correct one?
I think for example, I also thought about that before, but I think first, well, how to say this? I think that first it is improper that we simply say that the architects becomes a rule of selecting different generated results. I think that's not entirely true. I think a proper position would be, instead of focusing on one particular result, as designer, I think we are more focusing on the constructing this let's say design machine, like how this machine should work, or why this factor is important in this automated generated process. And then I think by that we still we still can talk about, we still can argue about our products, our results, despite no matter it is generated by the computer or not, because when trying to build up this process, we are still thinking about the different problems, and we are still making decisions by ourselves. It's not like we have a universal design machine and then it is
It learns already everything.
yeah. I think it's not like that.
Also, you could actually see it as all the process that you have been doing until now, they can be performed with the machine together. So like this smooth board that you have in the offices, usually you do it anyway, but what happens if you can have an overview of all the current spaces or houses or whatever that you're trying to design there. So this the machine can actually provide for you, and then you will also do it in the same sense. So you find your references, and then, for example, I'm working on a project that is actually trying to do this designing with the machine, which is you set constraints for the design. So you said I wanted to know that whatever is coming out, it should be structurally firm, so its tension and compression are fulfilled, so I don't have to worry about it. So these are the things that usually we don't think at the beginning, but then if this is already set, so then we don't have to worry. Then you only have to worry about what is it that you want to fulfill with your design. So then if you're constraining a space of design, you can make it smaller or bigger as you wish, but you are always in control on how you want to perform this design process. And it starts also with this motivation and what you want to have, what is already there. So you look at it in this mood board, and then you go to your design space, and then machine and you are there because she is proposing, or like not proposing, she is allowing you to see things that you maybe didn't know before, but you are still in control. So you're constraining the design space, in a sense.
You're more, and the architect of the future is actually designing a computer or a system, and rather than designing the space itself, it would be the computer that just generates something for you, which you had pre-programmed how it should be eventually. Maybe that's the question that he had. Is it giving you options that you can choose which one is more beautiful from? Because the architect is trained in finding beauty in architecture and designing space. But if you're just writing an algorithm, then you just generate space. It becomes generic at some point. So it's not necessarily designed architecture. It's just a design program or a designed algorithm to generate something that is most effective or most compressed or whatever it might be.
I think in the future one approach maybe is to design this algorithm, to design this process, but then still, the moment you are trying to make a design by this algorithm instead of by pencils and models, I think you are still thinking about the project itself. It's not just what you are thinking is the same. What you are focusing, what you are trying to address with your design is the same. It's just a different way of doing. This is what I
feel. It's a comparable situation to, you mentioned the Industrial Revolution, where you have a certain extent of standardization of certain elements, which would be similar with the technical revolution of this extent, where you standardize certain parameters or values. But still there would be a human creative force within us that will oppose this generic architecture. I mean, that's why there's already, or there has already been, a movement against this generic architecture in an industrial way as well, not even yet in a digital aspect, but that might again find a certain contraflow of an architect maybe.
I think also what is interesting to think is that there is a huge difference between code and algorithm, which for me it's interesting also to say it out loud. So for me, code is not always algorithm, but I can produce an algorithm. So code, in a sense, it's actually it's more in depth, it's more abstract. So architects, they need to be trained to produce code, which is the thinking behind how the thing goes first and why the thing goes next, and then how these are two related. But an algorithm, sometimes it's like more technical. So you use this function because it produces this, and then you have this output. And then thinking in this sense, it allows me to also think that as architect, I will not then only select, but I can also somehow help the machine to produce that. And then the selection I get will not be the one that I give it to the client. It will be something that I will also work on it to create it within this speciality of me as an architect for some of these.
So basically every architect has his own set of...
Yes, yes.
So do you think that that every architect and designer will become a programmer as well? Or the way I see it at the moment, that would maybe be also realistic, is that there is an interface, or let's say a program similar to, not similar, but in the way that Vectorworks today or ArchiCAD that we use, but we don't program. We just use it because it's an interface. And I'm not sure if there will just be programs like this which will maybe still allow some influence by the user, so change the parameters. Or do you think that the architects will become coders and or programmers themselves, make the programs themselves completely?
Well, it's basically you just have your own library. You just, it's like Photoshop, you tend to use the same tools again and again, and then you have your own style.
I think also, for example, now these computer engineers or coders, they are taking over. So if you don't know how this code function or how this algorithm performs, then you cannot control what is happening there. So I think we don't need to be an expert on coding. We just need to understand and to know what we want and how to get there. So it's not that you have to write the code from the beginning, it's that you know how to use a code that is there and then perform a task. So we are not experts in coding, we just know the libraries and we know what we need and how this thing works, so therefore we can put them together and then create something.
And I also think maybe in the future that every architect would more or less know how to code. It does not mean that every architect should be an expert in computer science, but instead, for example, for example, math, that, well, everyone knows how to do calculations, but then not everyone are mathematicians. I think coding will eventually be coding is a way of thinking, and also I think it will eventually be a way of doing, be a part of our literacy, be a part of our education, just like calculations, English, writings, and so on. This is what I think. But then this does not mean that everyone becomes computer science or computer science take over every field. Yeah.
But now it's happened. That is what is happening currently. So you go to the computer scientist to ask him, can you develop this? And then he gives you this black box that you actually don't know how was it built, but you just use it. And this is what ArchiCAD and Vectorworks and AutoCAD they have. So this is the interface, and you don't know how it's performing behind. So I think it's interesting to think that you can actually be aware of why are you using this and what is this output, and then if I change something, how it will influence on what I'm doing. So just to be aware and to know. And
but do you think that humans are not too lazy to want to understand? Because with our computers, they work. We can use them. We don't know how they work. I don't. I don't know if there is a program that helps me to design architecture that gives me a certain amount of control, where I feel that it's still my design, then maybe I won't have the desire to learn how it works in depth. And then a large amount of the result is determined by the programmer. I mean, I don't know, this is just something that I'm thinking about now.
but I think
this could be a possible development, but then, somehow the architects, they become less involved.
you mean in the
in this design.
in this I think they get involved differently. And Guo already answered this of laziness of human, what you addressed. It's like, what happened if from school you actually learn this? So it's like math and then code and then language and then English and then history. So it's not, because of course now if I have to learn the math I learned for 8 years in school, then it will be like, it's too much now, of course. And then I did it even like step by step, then it will change. Now then architects will use it because you learn it from school. And this is, for example, what our professor was trying to do. He did it already. So he was teaching the first years this way of thinking about what code actually means, how to apply it, how to apply it in architecture, what is design, what is architecture in the digital world, and this kind of stuff that if you learn it from your first years in architecture, then you know somehow, and then you can actually react and like have this way of thinking and argument, or if you don't agree, then why is it that you agree on, and like this kind of stuff.
Maybe we go to next.
You wanted to say something?
No, I just want to say, if like is that the interface, like we are supposed to, is data driven? I think to make new things, we need to know like how the process, because data driven. So we have all the data available. So of course you can choose, but if you want to learn how to make non-generic buildings and design, you probably need to learn the process and code and how the structure is, because otherwise it's just all the data that we do, all of us already have.
So you're addressing this to training data. So how the machines are learning currently now, they are learning from what we tell them to learn. So this data that I was saying that this is this entropic thing which is there, it's plenty, and the more we have, the less it makes sense, because you can never actually find what you're looking for if you have plenty of it. But currently we call big data because we have big data of a specific subject. So we already cut the data that we have in the entropic movement to one that is only containing something that will be trained, that will be used to train an algorithm. And so we have a colleague in our department who actually is asking this question. So Pierre, so what is it? Because we don't want, what happens if we do not want an answer that is within the training data? Because the machine will always answer within this framework. But what happens if you would like to train a machine with what you're thinking? So he is not having a training data, but he is actually training with his interactions with the computer, and then this will somehow learn his preferences. So
yeah, he was doing a complicated setup. So he, on the one hand, he measures the signals of our brain, of his brain, and then he's kind of doing interactive circles between him and the computer, so that the computer somehow the computer measures and somehow finds the patterns of his brain signal, and from that the computer try to find out what he likes, for example.
And so because the thing is that it's a scary, there is never, so I always have this, there is never I like and don't like. I think there is always a spectrum. So you may, like this Facebook thing, so you do it like this, you put a happy face, a heart, and like crying. So it's like you are never either like fully committed or like you hate it. So I think it's like in a spectrum, and you can never, when we had an experiment with a colleague that we had, it was called City of Indexes, and then we were trying actually to label places by liking or disliking. So it was hard actually at the end, because when you see a place, you may think, yeah, I like it, but it's like not so much. But this I like it a lot. So you can never capture this when labeling by these two binary ways. So that's why our colleague is trying to not find this binary binary movement, but then try to figure it out how his brain actually reacts to his. But like there is development in this kind of training.
I think.
Okay, so yes.
But still the question remains, And I just want to give one example. If someone in this room is familiar with investment banking, please correct me, but there's kind of artificial intelligence behind investments that we as human beings just can't do anymore, because it's about buying and selling a certain asset at microseconds kind of interval. And sort of here the decisions, as also I say, not only kind of the analysis and kind of the first elaborating part is done by a machine, but also kind of the decision-making process, should I buy or not, right? So what if, let's say, both processes, like the production process and kind of the decision-making process, are sort of, done by machines, and then the outcome at the end is that maybe it comes to, let's say, only a few people in the end, let's say clients or whatever, and the people that have political, monetary power to then eventually decide really sort of whether I want to have already very, very final results, because there have already been done a lot of micro decisions because we don't want to decide as human beings anymore. I know it was kind of weird, but you get my point.
I think, yeah. I think, no, I think it's not. I think this example does not means that that somehow we're out, because in your case, I would say the objective remains constant. I mean, the objective never changes. Therefore, the strategy and the method, I mean, can be optimized. But then the question is our objective, for example, in the case of architecture design, already fixed or not? For example, what is the objective? What is the object to design a house here? Is it for let's say minimum CO2 production, or is it for something else? I think this is the critical part, because I think for investment the objective is always to maximize the profit by selling and buying. So I think because the objective is fixed, therefore you can optimize the process. Therefore, the machine can somehow take over. But then, what happens if the goal changes? Then, yeah.
Because I think your example also falls in this engineering, in the field of optimization. Actually, what Guo was saying.
Open the window.
And so therefore, and then I agree that then you will have some tasks that will be eventually replaced by machines, of course, because they perform better. But in architecture and then in creative activities, then there are things that cannot be produced or done by machines. And we see it, and then, I don't know if you know this GANS algorithm, Generative Adversary Network. So this is an algorithm that is trying to generate images, or actually they are very good at generating images. So they are the ones that provide fake news, and then they create these in-between phases, but they are always doing it within this created framework. So they will never create a phase which is not within their training data. And this is what we are saying. So of course machines can generate things, but they will always be within bounds, and we can go beyond those bounds. And those are the tasks that are more in the creative side. And I agree that, no, I think that actually architects, they have to be involved from the beginning of the design till the end. Not only selecting, they should be involved from how do you decide, I don't know, what's the design purposes, and then at the end, what is that you're gonna deliver. So every steps that you're having it now, they should also be performed, but in different iterations with the machine. Okay, so we have the code part, so maybe we can have a break.
Or we just continue.
Or we can continue. It will take us like 20 minutes, or we can have a break and then continue after 5 minutes or 8 minutes or 10 minutes. So, continue? Okay.
Okay.
So we are going to show you the coding part. So we are calling this folding anything to anything. And first, just before I forget. So again, we're going to show you that everything that we are showing you in this lecture will always be uploaded in our website of the chair. And the lecture of today is lecture 2.
Yep.
So if you click here, you say allow, and you download it. And here you have a folder, and go to, because you should have Mathematica till today installed. Double click here, and then you access the code that we're going to teach you today. So please, if you can do this, maybe we can do it at the same time. And otherwise, so just to remind you what we said in the lecture, so about the bit. Right, I told you about these two differences between the bit. So the one that is the rendering or the graphics of it, which is the technical representation, and then the other one, which is the logical ground, which actually tells you whether it's true or false what you're performing in your computer. So the first one, we can call it it has a body, and the second one is the source of thinking. So we can take a digital image and unfold it into plain sequence of bits, and this sequence can be anything, because any digital artifact can be transformed into text, images, drawings, sounds, music, movies, and it can actually all the time be transformed back into numbers and back into any type of media. So we can say that we can transform text into images, images into drawings, drawings into sound, sound into text, so anything into anything. And just so when you download the code, I forgot this part, you have it like this. So when opening each of the titles, you just do a click in the arrows, and then you open them, just for you to remember.
Yeah. So so before Carla went into the the folding experiments, so the first thing we would like to introduce is how to work with Mathematica. So basically, this software, how do I exit the full screen mode? Yeah. Okay. So basically, this software, you create a notebook that contains text and code and whatever using this software, and then this software runs the code that are written in the notebook. And so everything that you will produce will be this mathematical notebook. So basically, this is the setup of this software, and so Mathematica is a programming language, and it is specifically designed for scientific computing and for research, for experiment purpose, so that you can do an experiment in a very fast manner, so that you don't have to bother different kind of things, like how to pre-process your data, how to visualize this kind of thing. So basically, it's a programming language.
And all the libraries are included already, so you don't have to download any library. You just have to download the software.
The software,
and then it includes every library that it comes as a function.
Yeah, and you will need some practice to manage. But then here I will show some simple cases as a start. But I will not go too many details. But I think that you should somehow, by reading the documentations, you should somehow try to learn it. So the basic part of any programming language will be for example, the data and the symbols, and in Mathematica this thing also exists. So for example, if I type simply if I type hello here and run this cell, so you press Shift Enter to run one cell, yeah, so and if you are curious, so here I'm not sure if you can see this part on the right part of the screen. So basically, mathematical file is organized by a sequence of cells, and then some cells are, for example, these cells has the style of input, which means the text written in it can be executed, and some other cells like here this text, number, and symbols, or here how to operate with Mathematica, it is with different styles, so that the writing here is not roundable. So yeah, but by default, if you type anything from the beginning, the cell is always roundable, so you can press Shift Enter and round the content of the cell. So basically, if you type hello here, and then the output will be simply hello itself, because here hello means a symbol. So you name this symbol as hello, and it contains nothing. And in Mathematica, if you put this hello into what's the
Square
name?
brackets.
No. What's
Quotation marks.
Yeah, if you put hello into the quotation mark, then this hello means a text, means
String.
yeah, it's a string. It's a string, and then it itself becomes a data, a string data, and yeah, and the code you write can also be a line of equation or computation, or for example, you write 1 plus 2, then the result will be 3. If you write 2 multiplied by 2, then the result will be 4. So these are some basic operations. And then an expression will be to give the symbol a certain value. For example, here I say hello equals to hello within the quotation mark, which means I want hello represent the data of hello, this text.
You can just put cat here.
Yeah. For example, I put cat here, then I run hello, it gives me cat. If I put hello in capital letters, then it gives me the result in capital letters.
I think you have to explain this.
Okay. And also, one thing to mention is here this semicolon. This symbol means not to display the result of this line. So therefore, for example, if I delete this, it will give me 2 lines of results. If I add this, then it will give me 1 line of results. So the reason of doing this is because I want to show the result by just calling hello itself rather than the computation. Yeah.
The expression you write, it works for the whole notebook?
Yes.
Okay.
Yes.
And it will always rename in order. So here he has 3 times hello, but the first was cat, the second was capital hello, and then now it's 1 plus 2.
Yeah.
So if you call hello now, it will be 3.
Yeah.
So it's sequentially.
Yeah. So the code you write later will replace the result produced earlier. Yeah. So if I say hello now, then it will be 3. But then these symbols are case sensitive. So if I type capital hello, then there's nothing. And for those empty symbols that contains nothing, the color will be blue. And so this is the basic expression in Mathematica. And then a very important data structure of Mathematica is list. So list is a set of objects which can be the same type or can be different type. For example, a set of numbers or a set of text, for example. And then the way of making a list is to type your data, to separate your data with commas, and then put all your data in what's this?
Curly brackets.
Okay, curly brackets. And for example, I make a list of 1, 2, 3, 4, 5, 6, 7, and of course I can say that hello equals to this list, and then the list can be a list plus, the list can be some numbers plus the list itself. So it can be anything. And one thing you should know about list is how to get the values, how to access the elements of the list. So in Mathematica, the way how you access it is by typing this square bracket twice. For example, I want the third element of this list, so I simply type hello with 2 square bracket and then a number 3. Then this gives me the number 3. So if I change here, if I say here the third element is, I don't know, something else, test, then I run it, and then I want the third element, it would be test. If I say I want the first element, it would be number 1, and so on. And the last thing is functions. So basically, functions is a pack of code that allows you to do certain operations, and most of the functions provide most of the operations that we need are already provided by Mathematica.
These are the libraries.
Yeah. And for example, for the most simple operations like 1 + 1, we got 2. And within Mathematica, these operations is actually realized by this function called plus. So if you type plus, square bracket 1, comma 1, and then this line gives you the result of 2. And also for certain computations, like I want the cosine of pi, I can do it in a similar way, so the result will be -1. And then I can also change here, for example, what is the sine value of pi, then it will be 0. And
I think,
yeah.
so if you want to know how to use the function, you just have to come with your mouse here and then click on this, and then it tells you to use it, you have to use the function, and then inside set is the element that you want to have the sign for. And then another thing is that when you come here again, if you go to E, which means information, and you click it, it gives you all the information of the function. And then here, it's very nice because you could actually type in here everything. So we saw it already. Sum, if we type sum, it will give you how to use sum, and then anything. So image, how to get an image here, like that.
And then, for example, if I want to convert a number to its rendering, for example, an image, then Mathematica provides us a function called rasterize, which convert basically anything to an image. Yeah. For example, I can say rasterize 3, then it gives me an image and a rendering of 3. And then for some functions, there are parameters that you can play with. For example, I can say rasterize equals to 100, then the result will be a much finer image of 3. Yeah, so basically all these functions, as Carla said, you can look at the documentation and to see how exactly they work. And in principle, coding with Mathematica is a process of learning, well, different vocabularies that you need to remember certain functions, certain vocabularies, so that you can actually write something. And you can always find the documentation by press, for example, F1, or you go to the drop menu and select help. And basically, Mathematica covers many different fields, and in most cases, what we need are already like packed with their code.
I think also there is one notebook, introductory notebook from Mathematica, that if you want to learn Mathematica, then if you follow all the tasks in this notebook, you will eventually learn it in this. So if you go here, you will learn it eventually.
Can you link, I don't know, for example, the rasterize tree, could you, instead of tree, link to another information on the...
Yes. Yeah, for example, you can say rasterize text, then it becomes...
Yes, but can you link to another information already in the notebook?
Yes.
Yeah, so for example, if you say I want to rasterize hello, which is the variable we have, then it's the list. But you know, it works like this because it reads the numbers as values for a pixel value.
Yeah.
So 0, and then like let's say hello. So it will read this as a pixel. So pixel will assign a value to 1, to 2,
Yeah,
and then
yeah.
it creates this image. Okay, so I think this will actually help to understand it better. So we said that we can actually fold anything to bits. So we have one example. We have this image. So if we do Shift Enter, and if we call here an image, we have the image, and then we create this variable saying image VW, which is black and white, and then I say I use the function color convert. Please function convert the image into grayscale, and then Shift Enter, and now if I say image VW, I get it, the image. So what we wanted to say is that anything can be transformed into bytes. If we said give me the image data in a byte representation, we get a grid that has 40 rows and 70 columns that we are seeing here. And if we ask for the 10th line, as Gu explained you from the data, we will get this line here. From the image. So you have to remember that these numbers here are the image itself. So each value that each number that you're seeing in the grid is 1 pixel in the image. Because if we ask for the image dimension of this, it tells us that it has as height 70 and as width 40. So these list of numbers are representing these 40 rows and 70 columns. So then we know that it can't, so we can see it as a pixel value, but we can also say it, we know that a byte is 8 bits, so we are gonna transform this byte into bits, saying, yes, thank you, using this function that is called integer digits. So now we're gonna have this representation of zeros and ones. And so all these functions that you're seeing that we are using here, then if you want to know how they actually work, you have to go to this documentation, and then it tells you please how to use it. So it actually it's not so important now to see how they work. It's just if we use it, we can transform this image that we're seeing here as a digital image into these binary representations of 0 and 1. So we know that it works fine for this 10 line that we take it from the data, and if we do it for the rest of the data, which it means it has, I mean, if we check the length of these n bits, it has this amount of values, and as we did with this with the number 3, now we tried also actually to represent these numbers as one image. So we have the width of the image, and then we say, because we know these are bits and we want to have it as bytes, so we say multiply by 8. So we have this image, which is not yet the image we had at the beginning. But if we want to go back from these numbers that we have now, that we can do many calculations, so we can these n bits that we have here, we can sum them, we can rest. So if we take only the first 10, they are these, and then whatever, we can do whatever with them. But for example here, to go back from these numbers to the image, we say we have this list, do a partition of 8 elements.
Every 8 elements.
So we run it, and here we have, so each of these are representing 1 pixel. And then we are doing the function which transforms this binary representation to pixels, to pixel representation. Here we have it. And then we go again.
This W.
So replace this W with width, and then you have it here. And the thing is that because we work with numbers, is that if we can already say for the list that we have, reverse the order, and it's like doing this mirror representation of the image. So you see it here. So it means that we can actually transform anything to anything. So we had one image which was a color image. We transformed it into black and white, and then this black and white was into bytes, then into bits, then into binary digit representation, and then again back to an image. So you just need to know and to work with those functions and to understand that you can transform anything to number space and then work with the machine. And the next is we wanted just to show you quickly this experiment that we go from images to sound. So we have again 3 images, and the idea here is that we are going to collect only the RGB values of each image, and these RGB values will be plotted in this list plot that we're seeing here, and by defining an amplitude and a given sequence, we can transform these plots into sound. So for example, here we have from the first image, we're gonna take the first image is represented like the first drawing we have here, the second one is here, and the third one is here. And if we want to select the sound for let's say one channel for each image, here I select the R, the red value from the first image, the blue value from the second, and the green value from the third, and then I set a sample rate. We can have
the previous
sounds. I'm being fast, but because we have to finish. But if you have any problem or any question, just write us. I will show you that actually it's sound. Okay. Like that. So you transform the images into sound. Yes, so we have to finish now. But if you have, as I said, any question, please write us an email or come around to our chair. We will always be there. So thank you.
Thank you.